Who doesn't like winning? I get the glorious task of coming up here and sharing some of these benchmark results that are face-meltingly awesome. So my name's Chad Sakac. I head up the field engineering team inside IonQ. That means I get the chance to work with many of you. I see a lot of familiar faces from around the world, and it's great to have so many customers and partners here. First of all, thank you. I want to start by re-emphasizing a point that's very, very important. In my travels, occasionally someone will talk about a feature like gate speed or qubit counts or those things, mostly because they're curious. But very quickly, they really don't care about any of that stuff. What really matters, as Ariel said, is the time to value, the time to solution. How long does it take for the algorithm to run? How much does it cost to get to that value, right? The Einride example of a 1%, 1.5% improvement, that has to result in a real TCO, right? Same thing goes with the things that we're doing with our friends at CCRM and everybody. So I also wanted to emphasize a visual for something that Ariel hit on briefly, which is that we are talking about the NISQ, or noisy intermediate scale quantum era, that these systems operate in today and provide real value, which you've heard over and over and over again. But in the NISQ regime, all systems have to do some form of error mitigation. So a very common form is lots of shots. I want you to have in your mind a picture, because I'm going to show you some data, and you need to have this picture in your mind. The IonQ systems, their shots are all grouped really closely. It's like a sniper rifle, versus shots that are all over the map, like something coming out of a shotgun with no choke, right? And that actually means something really, really important in the end, in what matters. I'm going to give a few examples. The first one is an optimization family of algorithms. These, in the benchmark harness that we published, these can be thought of as subroutines. They're used in higher level workflows and algorithms. So here we're talking about linear ramp QAOA. The QAOA family of algorithms are used all over the place. So again, I want to make this real. For example, when we were talking about the Einride optimization example, that was an essential subroutine in this particular case. But this occurs in all sorts of use cases. Financial services, you also saw bits of that inside Marco's discussion. You see it in bio-life sciences. You see it in even other forms of quantum algorithms where you optimize using the algorithm itself. In this case, we were 100 times faster. Just let that sink in. 100 times faster to getting to an answer of quality. I have to show graphs. So what do you see in this? We picked out one particular competitor, a superconducting architecture, and you can see that if you don't care about not being optimal, they are faster. That's over on the left-hand part of the chart. The bottom axis, too small to read here, but I just want to call out the crossover point is about 80% the right answer. So if you're okay with being 80% optimized, it's a wash. But if you want to be 100% optimized, we are 100x faster. And you'll notice that the graph, the blue line just stops. It's because we did 5,000 shots and they needed more than 1 million shots to get to that last data point. So we had to just mathematically extrapolate the rest out. Next example is an algorithm called a quantum Fourier transform. This, along with quantum phase estimation, are two of the most important subroutines inside this space that we're building. Not just today, but also in the fault-tolerant regime. It's a subroutine that's used in Shor's for cryptography. It's used in HHL, which is basically linear algebra solvers. So if you think about that Rolls-Royce ANSYS example that you saw from my colleague Martin, this is an algorithm that's essential for solving those kind of problems, right? And here, we were 1,000 times faster, 3 orders of magnitude. Again, the graph has a similar shape. Quantum Fourier transform is analogous to finding a needle in a haystack. If you have a giant haystack, how useful is it to not find the needle? Not useful at all. That's on the left. If you want to kind of sort of find the needle, you're kind of at the crossover point. Is that useful? No. If you actually want to do something useful with these algorithms, you have to find the needle. And to find the needle, the gap separates out enormously. And why is it? Again, just have in your mind that idea of accuracy over speed. If you need accuracy, you need way more shots, more than 1 million shots versus 5,000 shots, and you end up with a graph that looks like this. And of course, I have to have one more example, right? This is an algorithm called a hidden shift algorithm, again, developed by our very own Martin Rottingler, and it's a signal deconvolution algorithm. What the heck does that mean? It means that you've got a signal embedded in some noisy signal. The analogy here to make this make sense to everybody is, you remember how the Hubble Space Telescope went up and it was like, oops, the mirror has got some issues? There was some signal, there was like star images coming in, right? But there was also some bad signal, the mirror error. How do you deconvolute the good signal from the bad signal? Now again, we do this in hypercubes, in n dimensions. So that's a little more of a complex example, but the idea is the same. And if you look at this graph, same shape. IonQ is nice and flat. You can see it ramps up just a little bit there as we get to very, very high accuracy where we're pulling out the signal from the noise. But if you take a look, the superconducting platform basically goes almost asymptotic. You can see that we're actually giving them a bit of the benefit of the doubt. We kind of extrapolated the line out as if it was going to go straight. I don't know, if I'm a betting man, I would have bet that the line would have gone even higher. So who knows? Maybe we're not 10,000 times faster. Maybe we're 1 million times faster. We don't really know, right? This is a histogram of all of the shots, right? So the blue is the superconducting system and the orange is the IonQ system. What do you see when you look at the blue shape? A normal distribution, a bell curve. Also, it's a bell curve that is very beautifully symmetrical. In other words, the one standard deviation on the good side, which is over in this direction, is about the same standard deviation on the bad side, which is on this side. In other words, this thing was able to incredibly precisely act as a coin flipper. It's just as likely to be a little bit wrong as it is to be a little bit right. It's slightly shifted, the bell curve, like the whole shape, the mean is slightly shifted towards the correct answer than to just total randomness. But you'll also notice that there's almost no blue samples at the correct answer, right? So notice it just kind of drifts off. Conversely, the IonQ system has this strong shoulder where the shoulder is leaning in to the correct answer, which is 0. That means you've found the needle in the haystack, right? You're 0 distance away from the needle. By the way, this pattern, if I'd shown you all the histograms, it kind of repeats itself, and it's a reflection of this idea of the importance of accuracy. Is this always true? Is Chad always going to tell us that we're always the best? No. In fact, in the benchmark report, there's an example called this variational quantum eigensolver, and it's being used here to model a basic molecule. So you remember when Martin said toy examples? This is a toy example, but VQE as an algorithm is widely used. It was one of the earliest examples of an algorithm built for NISQ systems that have very low coherence times, microseconds, and very, very noisy systems. To just say, like, can we do something? Can we take a known energy state of a given molecule and see can we model it, right? Which also kind of implies it has limited utility. What does this graph show? Again, I'm not going to bore you. This is basically how much error do you have, and I'll give you the punchline. All the systems kind of sucked. Okay? All of the systems didn't accurately model this particular molecule's energy state. And in fact, it's even worse for us, if I phrase it this way, which is how long did it take for us to get the answer? The orange line is us. We're roughly 300x slower than the superconducting system at getting to the wrong answer, right? So why did we include this? We included this for a couple of reasons. One, we think it's very important to be transparent, and we've published this along with the rest of the results. Again, in my particular view, I think that the VQE and all variational algorithms, there's a broad family of them, are kind of likely to be of less and less value every day, right? But again, transparency is important. So we've shared that result. I'm in the middle of a twit-piss battle with somebody online who's vehemently arguing with me that we haven't shared the data, and I'm like, the GitHub repo is right there. You could literally run this on our system or anybody else's if you want. Now, you can never please everybody on the internet, but you got to scrap it out a little bit. So I'm happy to do that. And if you want the Kearney validation report that you heard about from Ariel, you can go and you can follow that QR code and see it. Now, I want to emphasize in the last few minutes here something that I think is important. All of this was about the NISQ regime. This matters today in terms of solving real-world problems with customers that you've heard about over and over and over again. But it also matters incredibly tomorrow. The core system architecture that you've seen from us, which is fundamental. Trapped ions are nature's qubits. The idea of a trapped ion has a very high fidelity because it's in this very tightly controlled Paul trap. We will take our record-setting 2-qubit gate fidelity that produces those accurate results today forward. But beyond that, we have more tricks in our sleeves. We're going to take our high connectivity benefit that we've had architecturally for years, and we're going to level up our game by being able to shuttle qubits around in future architectures, and by being able to execute gates in parallel. Being able to execute gates in parallel will have a massive effect on being able to run many of these algorithms. And when you add those together, it means that we will have not a little bit, but by orders of magnitude, 10x and more efficient low-density parity check quantum error correction algorithms. What does that mean? It means wider circuits, being able to work on bigger problems sooner. Not a little bit sooner, but years sooner than everybody else. And a hint on that, and it's a bit of a hint to what my colleague Rick is going to come up and talk about what we're doing with DARPA and with others. What I love is the way DARPA, in their quantum benchmarking initiative, framed the problem. Not in terms of show me your individual system components, but they said, here are some grand challenges. We want to simulate correlated materials. That is building on top of some of the examples of the code that we've shown you already. That's the evolution of the work that we're doing together right now. If you look at the advanced aerospace example, that is one of these linear solver set of problems. Fusion systems. How does plasma fusion work in reactions? Those are, again, the same class of problems. You know what those depend on? Quantum Fourier transforms and quantum phase estimations. These fundamental algorithms are coming up over and over and over again. And dynamic modeling is a combination of the QAOA family of algorithms, the QFT, QPE algorithms. Again, the things that we're talking about today are not only important today, but they're really important as we transition into the NISQ, out of the NISQ regime into the scaled fault tolerant regime. And crypto is, of course, the one that got everyone's attention on this. It's not new. You heard this from Niccolo right at the opening. We're happy that everyone's joined us in saying, hey, Q-Day's coming forward, and I want to highlight an example. This was a paper that was written in 2020, again by Martin, by Thomas Hayner, and several other people while they were at Microsoft. Everybody who has an umlaut in their name is now an IonQer. Now, what did this paper say in 2020? It said for elliptical curve cryptography, which is used in all cryptocurrencies, the core algorithm needs such a large number of gates, it's a number that's obscene. It's like 2 to the 26, right? And you need n number of qubits. That's how wide the circuit is to run it. And there's a little screenshot of just part of the circuit in here. What the team did is they said, you know what? We could actually improve on this algorithm, and they made an improvement in the algorithm that showed that it was 6,000 times less gates. 3 orders of magnitude, more than that, halfway to 4 orders of magnitude, right? That result only required 22% wider circuits, in terms of number of qubits. A huge efficiency leap. Why am I pointing this out? Algorithmic innovation itself is on an exponential curve. We're investing crazy heavily in it. I think we've got one of the best teams in the world, and we're doing it with many of you, right? It's not a we do it thing, it's an us do it thing, right? As we do this, that exponential curve, and it also is in the ecosystem. Inventions that occur everywhere are kind of shared. It's difficult to make this IP that is closed. What happens when you take an exponential function and multiply it by another exponential function? The exponents add. And human beings are really, really bad at exponential math. We don't think in those terms, right? So it means that we tend to miss stuff that is exponential, which means that the world is woken up to objects are closer than they appear in the mirror because these two exponential curves are both running. We've been saying this since Analyst Day. You need to act now. What do you need to do? You need to do that pyramid, right? Which is PQC at the edges, QKD everywhere you possibly can, and building in the idea of algorithmic crypto algorithm agility. We're doing it ourselves. We're doing it with our customers. If you want to talk about what we're doing internally, Mohsen, where are you in the room? Mohsen, these are there at the back. If you want to hear about our internal deployment story, go talk to Mohsen about this, and you should be doing this right now for you. This architectural advantage that results in what? 100x, 1,000x, 10,000x better time to solution is a speed and a cost advantage, not just today, but also tomorrow. Thanks, everybody. Thank you for being our customers. Rick, over to you.